Are there any questions or problems? Anything before we start? Okay. We'll talk about complexity analysis today, and first I'm going to talk about experimental complexity analysis. And actually, before I look at this slide here, I want to go into Visual Studio here, and I've implemented a binary search algorithm, and this is the code that tests it. So, get a little bit bigger. You see, all it does is it creates here an array that's sorted. It just puts the numbers from 1 up to size, or 0 to size minus 1. Then there's a stopwatch class in C#. So it creates a stopwatch, it starts the stopwatch, it does a binary search, it stops the stopwatch, and then it converts that time to milliseconds and returns it. So a very straightforward test. So if I run this, you can ask me, I've got 10 different things I can do, and what I just showed you is thing 1. So I'm going to run thing 1. And what it did was a single binary search on an array of length, I think it's 1023, for the last element in the array. So what do you think of that timing result? 0.13 milliseconds. That's what the computer says, 0.13. Is that right? That seem in the ballpark?
It's an array of what?
About 1,000.
1,000 numbers?
Mm-hmm. 1,000 integers, 1,023 to be precise. So it would take, that's sort of a worst case for an element in the array, so it'll take about 10 probes to find it. 10 probes, yeah. It's many order of magnitude too big. You know, the cycle time, it can do, at least 1 billion instructions a second or more. And this is a tenth, let's see, this is like a tenth of a millisecond, so it's a 10,000th of a second, as opposed to a billionth of a second, which is a nanosecond. So this is way off. So the question is, why is it so way off? Definitely does not take 0.13 milliseconds to do something so simple as comparing 10 integers and 10 array indexes. Yeah?
Is it because you didn't account for the warm-up for the CPU?
Okay, so for example, I fired up Visual Studio and then ran the thing. And what had to happen when I ran it?
Let's compile.
It has to, so the thing to realize is C#'s compiled twice. It's compiled once to the bytecode that's portable between machines. And then when it actually runs, it gets compiled again to machine code by a just-in-time compiler. So we've measured the cost of compiling the code. What else has to happen when I run the program? Yeah?
Maybe garbage collection from starting.
Yeah, well, yeah. Visual Studio has to initialize itself, and probably to make sure that it comes up fairly quickly, it doesn't completely initialize itself before it displays. So it may, when we click run, it may have to do some initialization. He mentioned it might need to do some garbage collection from that initialization. Who knows what Visual Studio is up to? What else? Yeah?
It has to go in with the DLLs.
Okay, it has to, it's probably dynamically linked libraries that need to exist when it runs a program, so it has to load them off the disk and get them into memory, yeah?
You have to print that line for the time.
Actually, that line is printed outside of the timer. Yeah?
Flooding everything in cache?
Okay. There's, it has a big memory footprint, does Visual Studio, and so everything, stuff has to get from the disk into main memory, from main memory into the cache, and stuff probably hasn't been made to the cache yet. Yeah.
Instead of saving the time before and after the method call, we're having a stopwatch run in the background during. Would that affect it?
You talking about like multi-threaded sort of things?
Yeah. Well, some aren't stopwatches asynchronous.
Yeah, I'm not sure about that. Okay, so there's no end to things that could have gone wrong. So you can't just write simple code, start the watch, time the thing, stop the watch, because there's a lot of stuff that has to go on for to reach sort of the full efficiency. All right, well, let's go back and look at my slide. Okay, so timing guidelines. And you'll be doing a timing experiment. I'll just tell you what you'll be doing. So the CADIS assignment for this week is simply to take my the algorithm from last time, the one with the jumble algorithm, the anagram algorithm, and you use that. That's the basis of your implementation for CADIS. And then I want you to do a timing experiment on it. So that'll be a second thing we'll do in the assignment. So you need to pay attention to this. You need to make your computer quiet. And what I did before class to make my computer quiet was I just went and killed every process I could find I wouldn't need during class. So and you need to look at the performance profile and see if something's going on in the background that's taking a lot of time. And, all right, so I've got OBS running right now here, which is taking 16%. So if I were really going to do a timing experiment, I would kill OBS. Now on a multi-core computer, one core could be busy, and maybe that doesn't matter. But it's good to get as little going on your computer as you can. Okay? Then I say warm up your code before taking data. Now, my feeling, this is my gut, is that you should run the code all the code that you're going to use for timing and testing for at least a second before you take any data with it. That gives the cache time to populate, and that gives the just-in-time compiler time to run, all the DLLs to be loaded and so on. Never time small intervals. Now, I found that students coming from 2420, I actually had a 2420 TA sit in this class once and argue with me because I advocated a different approach than is taken in 2420. Okay? So let me tell you what I mean. If you're timing a short-lived interval of time, it's not enough to time it once. Even if you've taken these other precautions, you can't just time it once and say that's the result. You need to time it a bunch of times. You probably believe that, right? Okay? What it comes down to is, so obviously you're going to write a loop. Let's say you decide you want to time it 1,000 times. So you write a loop 1,000 times, and what you do is inside the loop, you start the clock, you do the thing, you stop the clock. You compute the time that was done. And you do that, you add it all up, and then you divide by the end. Okay? I say no. Okay? Why do you think I say no? That's not a good way to do it. To time a bunch of small intervals and add them up. Yeah?
Maybe overhead from the starting and stopping the clock, get just one count?
Perhaps. There may be a little bit of overhead or error when you start and stop the clock. Think about it this way. Have you ever had someone take your pulse manually? It's getting rarer and rarer, but someone puts their finger on your wrist. What do? They go, your pulse is 60. Do they measure one pulse? No, they measure a bunch of pulses and compute an average. And they don't do this. They don't time one pulse and then time the next pulse and then time that pulse and add them up together to compute an average. So what you should do is time the loop. Write a loop that does a bunch of timing experiments, that does the timing experiments 1,000 times or 10,000 times or 1,000,000 times. Time the whole loop. Average that. Don't ever measure short intervals of time. The clock isn't that accurate. You may get an answer to nanoseconds. That doesn't mean it's accurate to nanoseconds. Okay? You're all looking dubious at me because you did things differently in 2420. Now, can you think of any reason? Yeah.
What about say you're sorting something? Do you have to shuffle that list again each time, right? Or would you just have to have a different list?
Okay. So let's say you're talking about timing sorting. And his worry is that we're going to, we've got to commute the array and then sort it, and we just want to time the sorting part. If we time the whole loop, we're going to time not just the sort, but the commuting that has to happen every time. Okay? So what can you do about that? Yeah?
You could write a standard array just before you start the timing loop, and then just copy that into a temporary reference in the timing loop, and then you don't have to permeate every time you just use that.
Okay, so you could create an array in advance, is what he's saying, and permute it, and then each time when you sort, you just copy the permuted array and use it. Of course, that takes time. Yeah,
You could do a different loop that just does the permutation and then subtract that from
okay.
the overall.
And in fact, that's what I'll advocate doing is, you've got your loop, time how long it takes with the sorting, and then take out the sort part and leave the permutating part in, and then just time how long it takes the loop to run without the sorting. So you get the average amount of time for a sort, the average amount of time with the sorting, and average amount of time without the sorting, you subtract, and what's left is the sorting. Yeah.
I found that when I in 2420 if I did the test and I would get the curve or line I was expecting as the complexity, but there would be little bumps all over it.
Mm-hmm.
I found that if I did it more times, like 2,000 times instead of 1,000 or 3,000 times, it would smooth out the more times I did it because of the averaging factor you were saying, where some background process in my computer that does what causes one little change in performance for a split second.
Mm-hmm.
I don't want that to show up if I
Right.
But that's what you mean when you say that when you say do it several times and put the timing at the beginning and the end. Is that something that's designed to help minimize the impact of sudden background processes or confounding variables?
Not so much that. It's just designed that we put too much reliance on the accuracy of the clock. If you're timing something that takes a few nanoseconds to execute, no way can you measure it with one of these stopwatches. It's just not that accurate. You've got to time a whole bunch in a row. You've got to time long intervals of time. So my rule of thumb is never time an interval of time less than a second. When you're timing something, run in a loop so that the loop runs at least a second, and measure that. And then divide by the number of times the loop ran to get your average. Don't time small intervals of time. Okay, and as we already mentioned, you've got to account for the loop overhead now, because you're measuring not just the thing you're interested in, but the running time of the entire loop. So figure out how long an iteration takes when you do the thing you want to measure, and how long an iteration takes when you comment out the thing you want to measure. And the difference is how long that thing you want to measure took. Now you have to be careful. I always worry about what happens if the compiler gets too sly and just notices that this loop doesn't really do anything, and just optimizes it completely away. That never has seemed to be a problem, at least when I run things in debug mode. I think the compiler is smart enough to see that there are actually timing calls that would depend. I'm never certain. Another thing you should do when you're doing this timing, yes, you're going to subtract away the timing overhead, the loop overhead, but you should make sure the loop overhead is as small as possible. So I like to display both the raw time, I'd like to compare the overhead to the overall time, make sure it's small. And this final point is, you need, depending on what you want to know, you need to interpret your experiment carefully. You need to design your experiment carefully. So, we've got my binary search algorithm. Suppose I want to know the average time for a successful search using binary search. How could I do that experiment? Right now, I'm just getting the average time to find the last element in the array, the largest element in the array. What if I want to know the average time for to look up, an element picked at random in the array? Yeah.
Use like a random number generator and just try and find that element in the array, time that every time.
Okay, so one thing you could do, let's say you have 1,000 elements in the array, you could just, in your loop that you're timing, each time through you pick a number at random and search for it. Pick another element at random and search for it. Pick another element at random and search for it. And time all that and get an average. What'd be a way to do it without a random number generator? Yeah.
You could do one test for each element.
Yeah, you could just look up each element once. And that way, you're not relying on the thing being random. You just look at each element once, and you do that. You look up each element once for as long as it takes to get an interval of time long enough to bother measuring. Now, a lot of times we want to see a curve that shows how the running time depends on the size of the input. So what happens when we double the length of or what happens when the array length increases? And here what I like to see is that you double the length each time. So let's say you measure an array of length 1,000. The next one should be an array of length 2,000, then 4,000, then 8,000. And I'll explain why a little bit later. Okay? So let's go back. Actually, before we go back, let me make that last point. So this is something that I talk about. I don't know if anyone ever uses this, anyone else ever uses this term. I like to think about the doubling behavior of algorithms, i.e. what happens to the running time when the input size doubles. So what I've got here is a function c. Think of it, this function describes the running time of some algorithm as a function of n, which is the input problem size. So that's f of n, and this is f of 2n. Okay? So I just plugged in 2n for n and simplified in some cases. And what I want to know is what happens when we go from n to 2n. So suppose that first row, suppose you have an algorithm that runs in constant time, and you measure its running time, which is c, and then you measure f of 2n, you measure its running time, and it turns out to be c. So how would you describe the doubling behavior of that algorithm? It doesn't change, right? So I subtract the two, and the difference is 0. So basically, it stays the same. Now, if you have a logarithmic algorithm like binary search, the running time goes from c log, if the running time is c log n for n elements, it will be c log 2n for twice as many elements. Okay? So how would you describe the doubling behavior here? How does the running time change when you double the number of elements? Yeah?
Don't you add log 2? So it's c log n plus log of 2.
Okay, so he's saying you add something. So yes, you add a constant. It increases by a constant each time you double the amount, double the input. So we can see that here. So what I'm doing is I'm subtracting the running time for 2n. I'm subtracting the running time for n from the running time from 2n. Log of 2n is log of 2 plus log of n. And when I simplify, I got c times log 2. Notice the base doesn't matter. It's just, it'd be a different constant depending on what base you use, but it's still a constant. So how would you describe the doubling behavior of a logarithmic running time algorithm? So if you want to complete the sentence, when the problem size doubles, what happens to the running time? Yeah, increases by a constant. All right, now suppose you have a linear algorithm. It goes, the running time for n elements is c times n, which means the running time for 2n elements will be 2cn. How would you describe the doubling behavior here?
Doubles.
Okay, it doubles.
It doubles.
And you can see this. This time I'm going to divide just because it works out better than subtracting. I'm going to take 2cn and divide it by cn, the running time for 2n. I'm going to divide by the running time for n, and that's just 2. So the running time it doubles. Now let's stop now. Why do you think I advocate when you're timing an algorithm that you double the size of the input each time? Go back there.
Because at this point, if we can clearly see, if we double it every time, whether it exhibits any particular behavior, and work backwards on that sort of thing we're doing.
It makes it great. It makes it really easy to figure out the complexity of the algorithm. If you double it and it stays the same each time, you're dealing with a constant algorithm. If you double it and it increases by a constant step each time, you know it's logarithmic. No curve fitting required. You just read it off. If the running time doubles when you double the input size, you know it's linear. Okay? So, what about this next one? N log n. So like quick sort or something, merge sort or something. So we've got Cn log n, and then when we double, we go to 2Cn log 2n. What's the doubling behavior for merge sort? Yeah?
Would it double and then add a constant?
Yeah, it's not quite that pure. So the best I can say is this. So when we do the division and work through the math on the logs, you end up with this mess right here, plus 2. Okay? And I got here just by, I just simplified, log of 2n is log of 2 plus log of n. So the question is, what's that mess? How would you characterize that mess right there? It's not, well, that's a constant. 2 log 2 is a constant.
But it's over a long run, so
But that's increasing.
it's going to get smaller.
So it's actually better than a constant. It just gets smaller with time. So the way I characterize it, it's 2 plus a little bit more. A little bit more than doubles each time. But as the n gets bigger and bigger, it gets closer and closer, just doubling every time. Yeah?
Okay, with the backwards working method, how would you characterize between a linear and an n-logarithmic?
Okay, that's a great question. So if you look at the data and you're trying to decide, okay, it looks like it's pretty much double. You never see it exact. In fact, I know someone has fabricated data on an assignment when asking to show the doubling behavior of something. I know they fabricated the data when it's perfect. Right? There's always a little bit of noise. And so it can be really hard to tell the difference between something that increases by a constant, that doubles each time, or that doubles plus a little bit more each time. Yeah,
Well, I feel like the behavior if the array is smaller is going to be more extreme. So
yeah, the behavior would be more extreme when it's smaller, but also the noise,
yeah.
because algorithms aren't purely log n. Merge sort is going to be n log n plus some linear term plus some constant term. And those low order terms become, can dominate until the n gets big. So it's hard. It's hard to tell the difference. Yeah?
So just thinking about the logarithmic graph, the logarithmic algorithms graphically, initially it's not always increasing by the same constant because there's an initial spike before it kind of evens out. So what accounts for that beginning?
No, there's no a pure logarithmic curve. There's no spike.
So does that graph illustrate an increasing by a constant?
Yeah.
Even in the initial doubling?
Yeah. With that up there, the C log n thing. Yeah, it's steep at first, but it's still just increasing by a constant if you measure it. See, the thing is, when you draw it, the doubling intervals get longer and longer, right? Let's say there's you go from 0 to 1, and then 1 to 2, and then 2 to 4. It gets bigger and bigger. So even though the curve gets flatter, it has longer to rise. Okay, so it's hard to tell the difference. I can give you 2 things to think about. First of all, you usually got an idea what you're looking for. And the other thing is, there's not that much difference between a linear algorithm and an n-log n algorithm. They pretty much look the same. Logarithm's slow enough growing that, it's, in some sense, it's almost a constant. Okay? So those are the words I use, doubles plus a little more. Okay? What about a quadratic algorithm? You double the size of the input, what happens to the running time? It quadruples. That division's easy. You just do the division, you get 4. So, when someone tells you this is an n-squared algorithm, or they use big O notation, and they say the upper bound on this algorithm is O of n squared, don't run for the hills and say, oh no, big O notation. What should you think when they say this is an n-squared algorithm? I mean, how should you visualize the running time of that thing? Yeah?
It's going to get exponentially worse as the year.
Right. Well, not exponentially worse.
Oh, not, I guess, quadratic.
Well, this is what you should think. Oh yeah, that means that when you double the size of the input, the running time quadruples. And so if you just measured it for a 10,000 element array and it took 10 seconds, you say, okay, so if I go to a 20,000 element array, it'll take 40 seconds. Okay? This doesn't have to be mysterious or purely theoretical. The gist of it is understanding this doubling behavior. What about if you got an n-cubed algorithm? Okay, n-cubed algorithm, if you just do that division of the two sides, you get 8. So it increases by a factor of 8 when you double. Now, what happens when you have an exponential algorithm?
That's where it gets exponentially.
Well, yeah, it does increase exponentially, that's true. But can we be more specific for this case?
Squares.
Yes, it's squares. So if you look at f of 2n, that's 2 to the 2n. If you regroup it, it's 2 to the n squared. Well, 2 to the n was just f of n. So f of 2n is the square of f of n. That's assuming the leading constant is 1. The math doesn't work out quite so nice when there's a leading constant other than 1. But the problem with exponential algorithms is, what happens if you time it by doubling the size of the input each time? Let's say 1,000, and then 2,000, and then 4,000. And the first time your running time is 10 seconds. What's your running time next time?
Way too long.
It'll be 1,000 seconds, 100 seconds. Then you do it again, it's going to be 100 squared, whatever that is, 10,000 seconds. You don't get many data points that way before you run out of life, literally. So if you suspect you're dealing with an exponential algorithm, just increase the problem size by 1 each time. Then what do you see? Doubles. So with an exponential algorithm, where the base of the logarithm, where the base of the exponential is 2, you increase the problem size by 1, the running time doubles. If the base is 3, it's going to triple and so on. Right? So we're after doubling behavior when we do our timing experiments. Yeah?
Is there one for factorial?
For factorial, well, let's think about what would happen. What would happen when you go from n factorial to n plus 1 factorial? Factorial is worse than exponential. Yeah?
N plus 1 times.
Yeah, it gets n plus 1 times larger. Because n plus 1 factorial is n plus 1 times n factorial. So you just get that extra factor of n plus 1. So when you go from 1 to 2 factorial, it doubles. The next step, it triples. The next step, it quadruples. The next step, it goes up by a factor of 5, and so on. That's why it's worse than any exponential, because the base keeps increasing in such a way. Any other questions here? Okay, so let's go back to my timing experiments. So that was, we looked at time 1. Now here's the second algorithm. Let's see what it's doing. We're constructing that sorted array again. And what I'm doing is, I am timing, I think repetitions, that variable is like 1024 or something is what I set it to by default. 1,000. So I am doing 1,000 binary searches, timing each one. And when you start and stop the watch, it doesn't reset to 0. So this is essentially accumulating all the time for all the binary searches. And then when I'm done, I do the division. Okay? So let's try that. So before, what did we get? Like 0.21 or something? 0.1. Okay. So that's the, why did we get such a lower number here? 0.00043, yeah.
You're only dividing your last measurement, not the combined total of all your measurements.
No, I'm doing. The way the stopwatch works is it accumulates time.
Okay.
But when you stop it, you're just pausing it, and then you restart it. Yeah?
It's true that we previously ran a lot of the same pattern. And when you're running in the fast times, if we wanted to do a caching and memory grab timelines.
Okay. I mean, we could think about it. I mean, the program ran longer, so it had time to get the cache loaded up and so forth. But it didn't run but it still ran a very short amount of time. It was only 1,000 repetitions. Okay, so 0.0043. All right, let's look at the next test. This is binary search 3. Again, we create the array, we create a stopwatch, and now I'm just going to time the loop. So before I timed a whole bunch of 1,000 measurements and added them together in average. Here I'm going to time the whole loop at an average. And this doesn't always work out for me. I hope it works out this time. So this is number 3. Okay, so not that dramatic as the first time. We went from 0043 to 0043 to 0038 as the average. So that's what I was telling you. I discourage timing something over and over again and adding up all the times. I encourage timing a long-running thing and then computing the average. Okay? Now, what can we do to improve this measurement? Yeah?
Subtract that from the time of
Right, there's some loop overhead, right? I'm timing this entire loop, so I'm also timing the time it takes to do this comparison a bunch of times in that increment. So my next attempt is this. So I compute the average as before, and then I do it again, but I time that loop again, but I don't do the binary search, so I'm just timing the loop overhead. And then I display both of them just as a sanity check before I return the difference. So I'm subtracting out the time it takes for the loop exclusive of the binary search. Yeah?
Would it work the same to have another stopwatch inside of the loop and then subtract your stopwatches every time?
Well, I don't want to put stopwatches in the loop because I don't want to time short-running things. I want to time long intervals. Yeah?
Would you worry that the compiler would just get rid of that?
Absolutely, I'm worried the compiler will get rid of that. But if it's going to do that, why would it be any different here? I'm what?
Because you're doing a binary search within the loop.
So I don't do anything with the return value.
And it's always the same index each time, so.
Yeah, it's a useless computation. An optimizer would just, except for these, hopefully it's clever enough to see that it really does matter, the time matters. I'm creating an array, I do not modify the array, I do nothing with the return value binary search, why not just throw it away anyway? So yeah, I'm not worried it's going to optimize this loop here away and not that one. I'm worried it'll optimize both away, but if it did, the timing would be 0. So I don't think it is. But it is something to think about. Okay. Let's see how this works, where I subtract off that time. We up to 4, I think. Okay, and so the total was 0.0032 this time. Last time it was 0.0038. That's just, what can you say? Don't get the same result every time. The overhead is, quite a bit smaller.